Hello everyone. In this lecture I will discuss Kepler's law of planetary motion. Kepler gives three laws to define the motion of satellite in the space along its orbit or its rotating path which the satellite follows. The first law of Kepler's, as the slide shows, the first law defines that in space any smaller body, or we can say a satellite in context of satellite communication, moves around the larger body, which can be either Earth or any other planet in case of any other satellite, in an elliptical repeating path called as orbit. So in the first law, the Kepler defines that any satellite in the space revolves around the Earth or any planet in an elliptical path which is called its orbit. Now, what is the situation of the Earth, or what is the situation of the satellite in its orbit? So here in the diagram I show an orbit which is elliptical in shape. Here in this elliptical orbit, this is our major axis and half of this is called as semi-major axis, which is generally denoted by A, whereas this axis or this part, means this horizontal line, shows the minor axis and half of this is shows as semi-minor axis, which is denoted by B. The situation of the Earth is it can be either on any of the focus of this elliptical path or this ellipse. So there are two focus points, F1 and F2 of this elliptical path. So Earth can be either on focus point 1 or focus point 2. So the shape of the orbit is dependent on the values of these semi-minor axis or semi-major axis. So the ellipticity, which is denoted by small e, which shows how elliptical the orbit is, can be defined as E is equals to under root a square minus b square upon a. So these values of a and b defines the actual shape of the orbit, that in case of a is equals to b, if a and b both are equals, the shape of the orbit will be circular. So this is all about the Kepler's first law. Now move towards the Kepler's second law. Now Kepler's second law defines that the satellite sweep out equal area in equal time in its orbit, or we can say the area sweep out by the line connecting center of the Earth and satellite must sweep out equal areas in equal time. As here in the diagram it shows time t1. Suppose at time t1 the satellite moves from time t1 to t2, and the area swept out by the satellite during this time transition t1 to t2 is a1, and suppose it travels a distance d1 by traveling from time t1 to t2. Further, from time t3 to t4 satellite sweep out an area a2 and it moves a distance d2. So if this time t1 t2 minus t1 is equals to t4 minus t3, then this area a1 will be equals to a2. So this Kepler's law defines that in equal time the satellite will sweep out equal area. This will be possible only if the satellite rotates at a variable velocity. So we can say that whenever the satellite moves away from the Earth, or it moves at the more distance from the Earth, its speed or its velocity will be slow. As it comes closer to the Earth, its velocity increases, or the satellite will be at its maximum velocity at the point where it is nearest from the Earth. So as the distance from the as the distance of the satellite from the Earth increases, its velocity reduces, and as the satellite comes closer to the Earth, its velocity increases. So the next Kepler law is Kepler's third law. This Kepler's law denotes that the time period, or the square of the time period of any satellite in its orbit, is directly proportional to the cube of the semi-major axis of its orbit. Or we can say t square is directly proportional to the a cube. By removing this proportionality sign, we can get the formula of time period of satellite in its orbit, which is t is equals to 2 pi under root a cube over mu, where mu is the Earth's geocentric gravitational constant and its value is 3.986005 into 10 to the power 14 meter square per second square. So from this law of Kepler, we can conclude that the time period of a satellite is dependent only on the semi-major axis small a, neither of the shape of the orbit. Suppose here I made 3 orbits of different ellipticity, but here the semi-major axis, or we can say A, is equal in all these 3 orbits. So the time period of the satellite in all these 3 orbits will be equal, rather their shapes are different. So the shapes of the orbit never affects the time period of the satellite in its orbit. The time periods only depends on the value of small a or semi-major axis. So if any orbits which have the same semi-major axis, so then there will be same time period of the satellite. Thank you.